Hello, everyone. This is a tutorial on how to do machine learning with InterSystems technologies. So welcome. Hope you enjoy this. What we wanted to do is just kind of reflect on Gartner's very good support or very good comments about InterSystems and our AI and ML technologies. You can see when they put us as a visionary in their magic quadrant, they listed this as the first strength, that we have dramatically enhanced our in-database processing of ML models with our embedded Python and auto ML capabilities. So we're going to touch on a variety of things that InterSystems does and can offer around integrating in support for AI and ML into our technologies, and hope you enjoy it. We're going to basically have 4 sections. There'll be 4 speakers going through this. The first is feature engineering, so how to take a data set and add features and sort of get it into the point where ML model really, or an ML technology stack really can consume it and train a model and all that good stuff. Secondly, we're going to train an initial model using integrated ML. So that will be our kind of beginning model. Then what we're going to do is go into Jupyter Notebook and into Python, use that data from Iris to train our own model, basically. And then we're going to incorporate both those models into an application using integrated ML in one case and embedded Python in the other case. And lastly, let me show you the application that we're focused on, that we're going to work with. So this is a hospital use case. You are running a hospital, and the census is basically the list of all the patients in your hospital. And you want to make sure that none of the patients in your hospital gets a stroke. So you'd like to know which of your patients have the highest risk of getting a stroke while in your hospital. And so that'll be a new column, a new sortable column in your census application called the probability of getting a stroke. You may think this is not a probable case, but the studies say that between, I think it's 2 or 3% and like 15% of strokes actually happen in the inpatient setting. So it's actually more common than you would think that patients actually get a stroke while they're in the hospital being treated for something else. So knowing about this risk, attending to patients that have the highest risk of stroke is a good thing to do as a hospital, and we're going to help with machine learning build that capability into this application. Okay, so with that, I'm going to turn it over to Marta. She's going to take the first section on feature engineering.
Thank you, Don. Hi, my name is Marta. I'll be taking you through the first section of this workshop, which is feature engineering using Iris SQL. And I might be a bit biased, but I do think that feature engineering is one of the most important parts of doing machine learning, because as the saying goes, if you put garbage in, you get garbage out. And even if your data is already pretty clean and in a good state, there is still a lot of value in using your subject matter expertise to do some pre-processing on it so that you can really get the most out of your machine learning model. So before we go ahead and work with the actual data that we have today, let's think for a minute about the kind of data that a machine learning model likes to receive. And the most important thing to grasp here is that we want to have what I call square data. So one single big table that has all of the information that we want to use to solve this problem. And each row within this table is going to be a unit of prediction. So each row is going to refer to one patient and one patient only. You can see that I have labeled the first few columns as capital X. This is what we call our features. This is all the information we have about the patient in this case. And then our last column is called lowercase y. This is what we call our label. This is the value that we are trying to predict, knowing all of the other information. And what the machine learning model is really going to do is it's going to find a function that relates our capital X to our Y. So a function that takes in everything we know about the patient and tries to predict the probability of stroke. Okay, so let's look at the data we have available today. As I mentioned, all of our processing today will happen on Iris SQL, and we're going to be working with two SQL tables, which contains data that is very similar to what you saw in Don's slides in the hospital census application. It is the same data that was displayed in there. I'm going to be showing to you the first row of each table. In this case, we have our first table is a list of patients. It's called stroke data raw. And for each person, we have some demographic information, such as their date of birth and whether they were ever married. You'll find out later in this workshop whether being ever married actually makes a difference in the probability of stroke for this specific sample set. So if you're curious, stay tuned. We also have some clinical information such as the height and weight, whether they ever smoked, and most importantly, whether they've ever had a stroke. We also have the zip code that they live at, which is very convenient because our second table just so happens to be a series of zip codes. And each of them is listed together with its corresponding location and with its residence type label, which can be urban or rural. Now, we are going to do a little bit of processing on this. First of all, we are going to join the two tables together by, you might guess it, matching the zip codes. And we're going to find out whether each patient lives in an urban or rural area, and we'll see whether that actually makes any difference for the probability of stroke. We're also going to use our subject matter expertise to compute some values that might be relevant. So for example, here we have the height and weight of each patient, and we'll use those to calculate the patient's BMI, which is a relatively common metric when assessing the overall health of an individual. Now, we could be calculating the BMI is an extra step. Of course, all of the information needed to calculate it is already within this table, but that might be a little too big of a step for our machine learning model. So we are going to give it a hand and pre-compute the BMI. Even if it's not technically new information, it's helpful to give to machine learning model data that is easily comparable. So a higher or lower BMI is intuitively more comparable than an expression, including height and weight. Same thing actually goes for the date of birth. Here we know that this patient was born on October 16, 2003. We might not necessarily care about the exact day or month they were born on, but we might be interested in their age because intuitively, as again, subject matter experts, we might guess that that will actually affect their probability of stroke. And so once again, we are going to be helpful to the machine learning model, and we are going to go ahead and compute the age and include that in our features. We don't really know whether either the age or the BMI will be relevant to predicting the probability of stroke. Maybe all that really matters is the height of the patient. That's okay. We are still going to give the height and weight to our model. We're just going to give it some additional information as well. And then the machine learning model will determine which features are more important, which features are more relevant, and it will use those to make the actual prediction. In general, volunteering extra information doesn't hurt. At worst, it's going to be disregarded. If you look carefully at this data now, you might notice that there is something amiss. The weight of this patient is 0 pounds. Now, what's going on there? Are they just very skinny? That's unlikely. Really, what's happening is that we have bad data, and that happens all the time when dealing with machine learning databases. So we'll need to handle that. There are a couple of different ways of doing that. We could estimate their weight based on the weights of other patients that we know, or we could just state that we don't know it and set the value as null. Now, all of these methods are acceptable. We'll just go with the simpler approach for the sake of this workshop. Okay, so to recap, our plan of action is computing the age of each patient from their date of birth, and we'll do that with respect to the date where the data was collected, which was the last day of 2020. That is when the information is current, and that is what we'll use to compute the age. Then we're going to include each patient's residence type into our features by joining the two tables. And last, we are going to use this formula to compute the BMI of each patient, and we'll take into account the fact that the weight of some patients is missing. Okay, so let's go ahead and get started with a hands-on exercise. You'll need to have a Docker desktop downloaded, installed, and running on your machine. If you don't have it, that's okay. You can go over to docker.com. and you can just download it and install it as usual. The second thing you'll need to have on your machine is the zip folder called ML-ISC. You can find that at a link in the description to this video. And you'll need to download it and then go ahead and extract it. Here it is. And if we open it, you'll see we have this docker-compose file in it. And this is all the information we need to download and spin up 3 container images using Docker Desktop. Okay, so let's go ahead and open our terminal. And I want to go to the directory where my Docker Compose is. So I'm going to go to my downloads folder. And then ML, let's make sure I'm in the right spot. Yes, Docker-compose is here. So make sure that Docker Desktop is actually running when you do this. And we're going to type the command docker compose up-d. And this will actually start our 3 containers. Now, the first time you do it, this might easily take 15 to 20 minutes, depending on the speed of your internet connection. That's because you actually need to download the 3 container images on your machine. Now, as you might guess, I have done this before. So the 3 images are already downloaded, and that means that Docker Compose will start in a couple of seconds, just like it did. If at any point during this workshop you feel like you've made a mistake and you want to start from scratch, you want to go back to your terminal and type Docker Compose down. That will actually take down the 3 containers and reset your environment, at which point you can go ahead and run Docker Compose up-d all over again, and that will create a fresh environment for you to work with. Okay, so now we have our 3 containers running, and one of them is our Iris container. That is a full instance of Iris running on your machine, and it already has all of the data for this workshop preloaded in it. So let's go over to our browser and navigate to our Iris instance. We'll find that at localhost-9092/CSP/sys. You can already see that pre-filling on my browser. %25 capital CSP.portal.home.zen. All right, and I am going to log in using user super user, and the password I'll use is sys, capital S, capital Y, capital S. You can use the same credentials to log in on your machine. And this takes us to our Iris homepage. So we'll scroll down to System Explorer, SQL, Go, and that takes us to our SQL view. We'll use the switch link to change namespace, and we'll jump over to the user namespace. And then we'll use the filter text box to filter by SQL user, asterisk, which leaves us with our stroke data raw and zip codes tables. Now let's drag stroke data raw here into this text editor and execute the query. And here we see the same data that we saw earlier in the slides. This is the patient list. Now I'm going to go ahead and nickname this table as lowercase a, and I'm going to explicitly say that I want to grab all of this information from table A. This is a little bit tedious, but it will make things easier as we actually do our processing. I can drag this text box to make it bigger. It's quite convenient. And we're almost done. Here we go. Let's try and execute this query. Everything looks good. And now I am actually going to join the two tables. So I'm going to join stroke data raw and zip codes. I'll say join equal user dot zip codes, and I'll nickname this lowercase v. And I'll join them on the rows where the zip codes match. So a.zip is equal to b.zip. And to show that this works, I'm actually going to include a value from the B table, which is the residence type. I want that to display right after the zip code. And here, sure enough, after the zip code, we see the residence type, urban or rural. Okay, so now let's go ahead and compute the age from the date of birth. I'm going to do a date diff, and I'll do that on a year value. And I want my first element for the date comparison to be the date of birth, taken from table A. And I want my second element of comparison to be my reference date. So in this case, 12/31/2020. And I will call this field age. We can now execute this query, and we'll see that next to each date of birth, we have the age of each patient listed. Now, last, let's use the height and weight to compute the BMI. And as we mentioned earlier, a lot of patients have actually a 0 weight in this database. We can see that right here. The first patient has a 0 weight, and then there's a couple more. So we'll need to take that into account. So let's use a case statement. I'm going to say that when the a.weight is equal to 0, then I want my BMI to be null. And instead, else, when we actually have the value, I want to take my a.weight and apply the formula, which is I divide it by the square of the height. And I multiply everything by 703. Okay, so this is the same expression for BMI that we had in the slides. I am going to take one more step and actually round it to the first decimal digit, just because that's generally how BMI is displayed. And then I'm going to end this statement saying that this value will be saved as BMI. Okay, let's execute this query. And here we have our BMI displaying next to the weight, and we can see that the field is null whenever the weight is 0. Okay, cool. So this is all of the pre-processing that we were planning to do. Let's go ahead and save our data so we can then use it in a machine learning model. I am going to save this as a view rather than as a new table, just to save on storage. This data set is relatively small. It's about 5,000 entries. So here space isn't really a huge concern. But if you're working on a real world problem, you probably have a much more extensive data set to train your model on. So I am going to create a view, and I'm going to call it stroke data processed. And I'll create it as the following definition. And I'm actually going to add one more field here into my selection, which is going to be the row number of the A table. So we'll call that A.%ID. This is literally just a plain row number, and it will come in handy later in the workshop. And I'll save that as iris_ID. I can press execute, and you can see here that the row count is 0 because technically 0 new rows have been created. But if we go here over to the views, you'll see that we have a new view called stroke data processed. And if we drag that in and execute our statement, you can see that our view has been saved here. It has the age, it has the residence type, it has the BMI for this patient. Now I'm going to pass the screen back to Don, and he will take the view that we just created, and he will use that to train an actual machine learning model. Thank you.
Okay, thank you, Marta. Okay, so now for the next section, we are going to build an initial machine learning model using Iris's integrated ML capabilities. And what integrated ML is it's basically automated machine learning that has been added to our SQL language. So there's a few new SQL commands that let you, from kind of the comfort of SQL, create a machine learning model based on your data. And what you would usually do is use this as an initial model, get a certain level of accuracy with your model. And then if that's not good enough for your use case, then you would drop into Python, like we will in our next section, and build a customized, sort of highly tailored model based on your data. So this is a good starting point to use integrated ML to build this initial model. So we will do that next. Now let's go back to our data here. So you can see the view that we just created in the prior section. It has all the new stuff like age and BMI and residence type, that kind of thing. And then we have our label column. So what we need to do, though, is we need to divide our data into training and test data. And the reason we need to do this is with any machine learning model, you really have to know how accurate it is before putting it into production or even determining whether the model is useful or not. And the only way to measure accuracy of a machine learning model is to separate out your data so that you're measuring on data that you did not use in training. So you have to have a training data set, which is usually about 80% of your data. And then you need a testing data set or a evaluation data set or some kind of word like that. And that's usually 20% of your data. You train on the 80%, and then you take your model and you test it on this unseen data, this last 20%. So the way we're going to do that is actually, we're just going to take this iris ID column, and if it ends in a 0 or a 1, we're going to call that our evaluation data. And if it ends in a 2 through 9, we're going to call that our training data. So that'll give us an 80-20 split that's roughly random if you consider this iris ID as just sort of going in order there. So the way we're going to do that is to create 2 additional views. So create view. I'm going to create my evaluation data first as I'm going to select star from this data, from this view. Stroke data processed, and we're going to use the mod operator. So that takes a column name. We're going to mod 10, which means just take the last digit. So kind of get the remainder after you divide by 10, we'll get rid of the other digits. So if the mod 10 is in 0 or 1, then we're going to call that evaluation data. Seems like I did a good job there. Not quite. Processed. Okay, so that's our evaluation data. We can check it. Select star. What's the count? Star from stroke eval. To make sure it's about 1,000. There's about 5,000 in our whole data set. That looked good. And then we're going to create our training view. Stroke train as select star from stroke data processed, where same thing mod will be greater than 1. What did I mess up here? Need to know the divisor there. Okay, so that seemed to work. And let's just count. Let's do another count. Select count. I think you're supposed to do 1 like that. Select train. And that is 4,000 rows. Okay, so we've divided into 80, 20. So that's kind of step 1. Now we're going to use our 4 new SQL commands, basically. Actually, 3 new commands and then a couple new functions. So the first thing you do is you use the create model command. So this will create a machine learning model. We'll call it stroke model. And you need to tell it the column that it needs to learn how to predict, which is the stroke column. And then you need to tell it, you need to give it some table that has the columns of the rough structure. So we'll give it our training table. If you execute that, it'll just create the model. So that'll be quick, doesn't train the model quite yet. So now we have a model created. The second command is to train that model. Actually, let me just edit this. So that's the train model command. You're training on the stroke model, and then you just have to give it a name as stroke. Let me just call it stroke model train. Okay, so this will go do the training. So in this case, the training should take around 16 seconds. So you just need to be patient. You can count to 16 or 17 or something like that to pass the time. But that's about all you need to do, and it's going to train this model. Okay, so now we want to validate the model on the validation data. So this was trained on the training data because you specified that when you did the create model. So the train model just adopted that. Now we're going to validate that model, which will give us a number of metrics. Let me pay attention here. Validate model. So you have to give the model that you want to validate, stroke model, give the validation a name, stroke validation, and then which training run do you want to use? We just have the one using stroke model train. So that's the trained version of the model. You can have multiple training runs, which ends up being multiple trained models using stroke model train from stroke eval. And then lastly, you specify the data that you want to do the evaluation on. So we're going to do it on our evaluation data, just the 1,000 rows. So this is relatively quick. It's using your model to make a prediction on each of these 1,000 rows. And then it calculates a bunch of metrics based on that prediction. So the way to see those metrics is you do a select star from information schema dot ML validation metrics. Okay. Now we can see that our model got basically here are the 4 metrics. It says a precision of 28, a recall of 60 or 0.28, 0.60, an F value, F1 measure of 38, and then an accuracy of 90%. And the best number for each of these is 1, basically. So I will explain what a few of these mean in a moment. But that gives you kind of your accuracy of your model. Okay. And the last thing we're going to do is just make some predictions so you can see what they look like. So for this, we're going to select stroke. I'm going to put that column first, and then all the other columns last. And then you use 2 new functions. So one function is the predict function. Predict. And this, you have to specify the model, and then the version of the trained model, stroke model trained that you want to use. So we'll call that as prediction. And then a very similar function, which I'll describe the difference in a moment, called probability. And we'll say probability. Leave that there, and we'll do a from stroke. We're just going to do our predictions on the evaluation set. Okay, that worked. No typos. So what you see is, your regular columns here. The stroke column is repeated at the beginning. You see what the model predicted is 0 or a 1. You can see it's getting it right a lot of the time. The 0, 0 is a 1, 1, and then you can see cases where it's getting it wrong. And then the probability that this patient is going to have a stroke. So a number between 0 and 1. The higher value, the more it's going to predict stroke. And I'll show you the correlation between those 2 columns. So the other thing I sometimes like to do is order this by the probability descending. This will take a sec because it has to do a prediction on everything and then do a sort on this. And you can see the highest probability it gives anybody is a 53%. You might wonder why it's not near 100%. It's very rare to get a stroke. So in this data set, for instance, only 5% of patients actually have a stroke. So predicting I guess the average probability then would be 5% or so. So it's pretty confident in this first group. So you can see the probabilities here. You can see that everybody with a top probability is predicted to get a stroke. And if I scroll down, you can see eventually it turns to zeros. So what the model has done also is it's established a cut line. So everything above 14.1, let's say it's predicting will get a stroke, and everything below 14.1 is predicting will not get a stroke. Okay, so that's so the difference between these 2 columns is the probability just ranks everything. Then the model will pick a cut line, and then everything above the line gets a prediction of 1. Everything below the line gets a prediction of 0. Okay, what you also like to see is the beginning of this table is where you want all your actual strokes. So that's what this first column is. So you want to see all ones or a lot of ones here. That's how you would know your model is working. So you might say, well, this doesn't look that great. But the reality is, if only 5% of patients are going to get a stroke, then you would expect every 20th row to be a 1 if all the stroke patients were evenly spread out through the data. And you can see that it's much more frequent than every 20th row getting a 1 here. So it's done a very good job of sorting the real stroke patients near the top of the list. And if you want to go to the bottom of the list, you can, and confirm that you have a bunch of zeros on the bottom. And indeed you do. So it's sorted the ones near the top, the zeros near the bottom, ranked by probability, and that's what you want the machine learning model to do. Okay, so now we have an initial model. Let me explain the accuracy measures a little bit more, and then we'll drop into Python for the next section. Skip this. Actually, let me just explain this. So under the covers, this integrated ML feature uses AutoML libraries. And in this case, we use the H2O.ai library. So this is a leading edge library. And what it does is deals with nulls, it transforms category features, it standardizes numbers, things like that. It tries multiple types of models, boosted trees, logistic regression, neural networks, that kind of thing. And then it will kind of have this leaderboard, and then it will start to ensemble, kind of average multiple models together and throw the ensembles in the leaderboard until it finds the best, highest performing model. Now that whole process only took 17 seconds, as you saw. So it's a quick process, but it gets a pretty good model because of these AutoML techniques. Okay. So you might just think all you need to evaluate model performance is this accuracy metric, like how many times did we get it right? But the reality is accuracy is not a very good metric for a needle in a haystack problem, which this sort of is. Only 5% of patients actually have a stroke, so it's kind of a needle in the haystack problem. So one thing you could think about is, well, how might you build a model that has a 95% accuracy? Well, you could simply predict that nobody gets a stroke, and you would get this great accuracy number. So for this reason, this is not a very sensible, a good metric to evaluate machine learning models of this style. And by of this style, I mean kind of needle in a haystack style. So there are a couple other metrics which are more important for this kind of problem and are useful for all problems, actually. So recall and precision are important, and I'm going to describe these in a moment, are very popular metrics, especially if you're predicting whether somebody has a stroke or not. In our case, we're focusing on probability of stroke for our kind of patient census list. And the metric that most people use there is called area under the curve, or area under the ROC curve, receiver operator characteristic curve. So I'll describe a little bit about that as well. But actually, when I talk to people outside of machine learning, I use the AUC metric, but I use the word accuracy. And you can often see this in the press when somebody says they have a 95% accurate model. You dig into the actual paper, and they're actually referring to AUC. So, but accuracy is a good way to think about it in a non-mathematical way, meaning 90s are good, and 80s are pretty good, and 70s, 60s, you start to get into the not so good territory. So the kind of way you think about accuracy is the way you would think about AUC, honestly. Okay, but let me describe precision and recall real quick. So a confusion matrix is kind of a way to put down your numbers that recognizes there are two ways of being right and two ways of being wrong. And these metrics, having these 4 different kind of numbers, matters in that way. So you can be right that they had a stroke. You can be right that they didn't have a stroke. You could be wrong and then you predicted a stroke, but they didn't, and you predicted not a stroke, but they did. So this kind of lays it out. So in this case, we made 1,022 predictions. We correctly predicted that 30 people had a stroke, but we actually made 107 predictions. So we actually thought personalizing the machine learning model, the model thought 107 patients had a stroke, but only 30 did. But on the other hand, of the 53 patients that actually had a stroke, we found 30 of them. So this concept that I just verbally went through is recall and precision. So recall is the number that you correctly found out of the total number of stroke patients. So in a sense, you recalled 57% of them from the pool. So if you picture these 53 patients are in this pool of 1,022 patients, you recalled 30 out of the pool with this machine learning model. Precision is based on all the guesses that you made, how many were correct, guesses of a stroke. So we guessed 107 people had a stroke, and 30 of them we got right. So precision is basically the 30 divided by the 107, 28% as a precision. Now these work against each other. So if you think of that threshold and you lowered that threshold, you would find more real stroke patients. Your recall would go up, but your precision would go down because you'd be predicting more than 107. Okay, so or vice versa. If you're more selective, so you move that threshold line up, then you're going to find less of the stroke patients. So you won't find 30, you'll find 20 or 10, that sort of thing. But on the other hand, you won't make as many guesses, so your precision will probably go up if the model is good. So these kind of work against each other, and that decision of what the best threshold is really a conversation with your subject matter experts, your customer, depending on the use case, and whether you want to find everybody at the risk of false positives, or you want to sort of optimize the precision in a sense. So don't guess as much, but be more confident and accurate when you do guess. Okay, so that's a combination. That's sort of a trade-off that you need to decide. And the one other metric, I'll just describe how to read it, and so you can see it. But I won't describe how to calculate it because it takes too much time. But at any rate, the other one is the AUC, which is the area under this curve. The curve is the true positive rate on the y-axis and the false positive rate on the x-axis. And a perfect model would have an area under the curve of 1. So it would kind of fill this whole box if you drew that area. And in this case, based on drawing the threshold at different levels, where you have different false positives and true positive rates, it ends up drawing that line, and the area under that curve in this case is 0.87. So that's pretty good from a quote accuracy point of view, but it may not be good enough for your use case. So what may happen next is you might want to build a machine learning model yourself in Python in a Jupyter Notebook, which is what we'll do in the next section. So Agustin, I'll turn it over to you.
All right. Hello, my name is Agustin, and I work at the Release Engineering Department of InterSystems, and I am excited to show you part 3 of Machine Learning 202. So, assuming you have your Docker instance running, which I would assume you do, go ahead and go to localhost:4200 in your browser. That is the very first step. So this will take you to an interface that looks like this. It prompts you for a password, and the password is admin in all lowercase, so ADMIN. I'll go ahead and type it up here so you can see. It's just admin. So we'll log in, and we can begin playing with our Jupyter Notebook. I actually have to restart this because I just ran through this. So let's go ahead and delete this. You can ignore what I'm doing right now. Okay, so the very first thing we're going to do is upload the notebook. So what we need to do first is navigate to the root of our directory located here. We'll click onto this icon, and then we will hit the upload button located here. So we're going to upload part 3 student v6.ipynb and hit open. So this will bring it up in the interface and allow us to begin interacting with it. You may or may not already be familiar with Jupyter. So Jupyter is Python. It's just Python, except that you can run it incrementally in blocks, and you can also annotate different parts of the notebook using Markdown. So we're going to be going through this together. We have different code blocks that we're going to be interacting with. And all of these code blocks have context written above them in Markdown form. You don't actually have to read all of the context. I'm actually going to audibly explain it out loud to you. The context is there, though, if you want to, pause the video and, read for yourself what's going on with a given block. So the very first thing we're going to do is import some critical libraries. So we're going to be importing pandas, NumPy, and pyplot. So these are Python libraries that are very good at handling databases. That's pandas. NumPy is very good at matrix math, and pyplot is really good at plotting things. So in order to actually run this code block, we hold down Shift and hit the Enter key. Now, what happens when you do this is you'll see an asterisk for a moment. You might have noticed it on my recording. And then you'll see a number. So this number represents the order in which you ran the blocks, and the number will appear upon completion of the block. So we know that this block finished successfully because we can see a 1 here. We imported those libraries. We don't have any output because Python doesn't normally print anything out when you import those libraries, or any library for that matter. And the next thing we're going to do is import iris. So we go ahead and run this code block here, and we have imported the iris library. Very cool. So the next thing we have is a variable called answer here. So answer here basically works as a fill in the blank. So anytime that you see an answer here, it is effectively just backspace me and replace me with the answer. And you'll see that in a moment. But we'll go ahead and run this code block just to define that variable. So we have our libraries imported, and now we can actually go ahead and analyze our data. So the first thing we're going to do is connect to our iris instance and put the data that we just ran through with Marta and Don, and we're going to put it in a pandas data frame called stroke df, or stroke data frame. So the first code block here defines the way by which we connect up to the server. And the next code block actually connects to the server and puts the data into the data frame. Now, if you try to run this without doing anything, answer here will break it, which is on purpose. But instead, we are going to replace .answer here with .head. So your code block should look like mine. It should say stroke df.head. And then we can go ahead and run this block. So you'll see it runs for a second. That's it connecting to iris. And then it takes our data and magically puts it into this data frame. And it's great. It works very, very well. And we can use this head here to basically take a sneak peek into our data. So we don't look at it at large. This isn't necessarily a way by which we, gauge overall statistics of our data frame, but instead a way that we peek into the columns and see the different values stored inside. So our first 5 patients, they happen to be 4 women and 1 man between the ages of 13 and 55. We can see here that none of them have hypertension or heart disease, so on and so forth. We can also see what kinds of values exist in these different columns. So age is an integer, which makes a lot of sense. Ever married is a category between no and yes. You also have other categories like the residence type, rural versus urban, or gender, female versus male. You also have floats. So the glucose level is 85.81 or 108.89, so on and so forth. Different types of data. So once we have our data ready, we can actually go ahead and get it ready to feed into our models. So in a lot of schools of math, X tends to represent input and Y tends to represent output. So turns out, for our purposes, it's very similar. So we're going to be giving the model values like gender, age, if this person's ever been married, hypertension, stuff like that. And the corresponding Y, or output, that we're asking our model to work with is stroke. By the time this data was collected, did this person have a stroke? And those are our labels. So fun ML fact, not all machine learning models actually need labels. In fact, there is a whole school of machine learning called unsupervised learning, where you have to basically teach a model how to cluster things together without labels. But we are working with supervised learning. So we're going to hand the model a patient, and we're going to say, here's the patient, here are all their attributes, and this is the label. Turns out this person did not have a stroke. And so over time, based on the attributes of the different patients and whether or not they actually had a stroke, the model will learn what a stroke patient looks like over time. So we go ahead and run this block to define our X and Y, and then we're going to split it up even further. So Don probably already talked about this, but training versus testing data. So we are going to give our training data 80% of the overall data. So this means the model is going to train itself with 80% of the patients, and the remaining 20% will be delegated off for testing purposes. The model will actually never see that 20% until it comes time to test. You can compare this to, helping like a kid practice for a math test. You hand the child, a bunch of practice problems, and then when it comes time for the test, that child will be tested on problems they've never seen before. It's more about recognizing patterns and being able to tackle unfamiliar problems than it is about memorization. And that's why we parse the data out into two camps, 80 and 20. So for train_size, we're going to fill in a value of 0.8. So we're going to backspace the answer here and put a 0.8 in its stead. And for random state, we're going to put in 42. Some of you who might be well read know where that value comes from, but random state basically just makes it so that any two models with the same random state, assuming that they have the same hyperparameters, aka human controlled properties of the model, they will perform exactly the same way. So we're having you put in random state equals 42 so that my model behaves exactly the same way that your model does, and it's good for testing purposes or for teaching purposes. So we'll run this block. It will do a little bit of divvying up, and we have made our two different camps: our X-train X-test and Y-train Y-test, which I guess is like 4 camps. But anyways, we're going to use .head to see the patients that landed in the testing data. So if we run this block, we can see our first 5 patients in the testing data. So we can see that 2 of them are men and 3 of them are women. They're between the ages of 0 and 65. None of them have had hypertension or heart disease, so on and so forth. You can see that we're giving the model their different attributes, but we're not immediately giving the labels. We're going to feed those alongside these rows in the Y-test data. So if you would like, you can backspace X-test and put in Y-test instead. And if you run this block, we can see none of them actually had a stroke. And we can see their corresponding ID numbers within the data. So we have our data ready. Now we can go ahead and put it into our models. So we're going to be using a library called XGBoost. So XGBoost is a very popular library for this exact problem, or for any problem that uses categorization. And we are going to be using something called a gradient boosted decision tree, which sounds really fancy at first, but I promise you it's actually a little bit more simple than you think. So a decision tree is something you're probably already familiar with. It's basically like a choose your own adventure book. So in the model's case, it's going to take all these patients and it's going to put them in forks in the road. So let's say, for example, the model decides to make a fork where a patient can either be above or below a BMI of 30. So if the patient has a BMI above 30, we're going to push them down the path towards a higher likelihood of having a stroke. If they have a BMI below 30, we're going to push them down the path of being less likely to have a stroke. And then once we get to the next fork, we might push them back up to a higher likelihood or even further down to a lower likelihood or whatever. But there are basically a series of decisions that the model decides to make on every patient that will inevitably land them in some kind of category. So ultimately, at the end of all the decisions, the model will look back at all the forks and it will say, this is a patient who has this percentage likelihood of having a stroke. It uses decisions or forks in the road in order to do that. The gradient boosted basically means that the model takes individual trees, because the model will actually compute multiple decision trees and pit them against each other. The gradient boosting basically takes the errors of multiple trees and kind of combines them together to figure out where these trees are going wrong and makes ultimately a much more powerful tree based on those errors. So if you're more curious about exactly how this works, you can actually click some of the hyperlinks in the notebook. We have this one up here that just takes you straight to their website. This one over here that takes you to a Medium article about, what decision tree you might want to use, so on and so forth. There's links if you want to check them out. So the very first thing we're going to do is import the XGB classifier model. So we go ahead and run this block. Simple as that. We're going to take it from XGBoost library, import XGB classifier. The next thing we're going to do is we're going to alert the model preemptively about which columns are categorical. So this includes gender has a male, female, or other. You have residence type, which includes urban or rural. And this type of model, XGB classifier specifically, is totally fine with working with categorical data. It just needs a small heads up. So that's what we're going to do with this block here. Cool. So now that we have imported this model, we can actually go ahead and try creating a few. So first, we're going to define a model, and we're going to just name it model, which is very creative. And we're going to give it a few hyperparameters, which you can actually see up here in the explanation. So for the N estimators, this is basically how many decision trees the model will make and pit against one another. So we're going to have it make 2 trees. So we'll put N estimators equals 2. We'll give it a max depth of 3. And this basically means how many forks in the road is this tree allowed to make. And we'll give it a learning rate of 0.01. So a learning rate of 0.01, basically, for those of you who are, calculus nerds, this is how fast the model is stepping down the loss gradient. In other words, it's how fast does the model learn from its mistakes. And this is a bit of a Goldilocks variable. You don't want it to be too high, and you don't want it to be too low. If it's too high, the model will learn too fast, and it might actually hone in on the incorrect problem. And if it's too low, then the model won't learn at all. So we're going to put it at 0.01 because that's a pretty comfortable place to start. So we'll go ahead and run this block. We create this model called model, and now we can actually start working with it. So this isn't a very powerful model. We're giving it very basic hyperparameters to work with. So let's see how it actually performs. So let's run this next block here, model.fit xtrain and ytrain. And this is essentially training our model with the training data. I don't know why I put training in air quotes, because that is literally what it's doing. But if this model, or if this code block runs successfully, you should see this light blue block appear underneath it. And then we can actually run this block to create this preds proba array. So this will take all of the patients in the testing data and ask the model, hey, how much of a likelihood do you think that this person will have a stroke? Do you think it's high? Do you think it's low? What do you think is the exact percentage that this person will have a stroke? And the model will give some answers. So before we actually go into what the different risk scores are, let's try computing the AUC. So Don probably already explained this, but this is basically saying it's like accuracy for a needle in the haystack problem. If we wanted just raw accuracy, we wanted the highest accuracy possible, it turns out the patients that are in our testing data, only 41 out of 982 patients, something like that, actually had a stroke. Which means if we made a model that simply predicted that nobody ever had a stroke ever, it would get an accuracy of 95 point something percent, which seems great on paper, but that's not what we want. We want to know how good is this model actually at predicting if a given person is going to have a stroke? That's why we use AUC. It's like accuracy, but it's a little bit better for needle in the haystack data. So the arguments we're going to feed in here are going to be y-test and preds proba respectively. So let's backspace answer here. This first one and put y-test, and the second one we'll do preds proba. Let's go ahead and run this block together. And we see that we get an AUC of 84.29%, which seems great. Like that's actually a pretty good AUC for a pretty basic starting model. But is this actually a good model, or is it getting lucky? So before we do this next code block, let's figure out what constitutes a good model. A good model would have strong opinions. A good model would be able to look at a given patient and be able to say, I think this person has basically no likelihood of having a stroke. Or I think this patient has a very high likelihood of having a stroke. But it would be a model that has opinions. If it were given somebody who is very young, who has never smoked before, has no history of hypertension, and a very healthy BMI, person's probably not going to have a stroke, right? So it would give that person a low risk score. But let's see the actual risk scores that it assigns to all the patients in the testing data. So if we run this next block, we can see the range visualized. We can see the highest risk score we got for any patient was a 0.4965, give or take. The lowest was a 0.490. So the range here is tiny. The lowest risk score it's willing to give and the highest risk score it's willing to give are barely anything apart from each other, which means that this is not a very opinionated model at all. So it turns out our model was in fact getting lucky with the AUC. So how do we make a model that does better? Well, we could compute a much fancier model, and that's what we're going to be naming this model, by giving it much more powerful hyperparameters. Now, you might notice that these hyperparameters are incredibly specific. Like the learning rate, for example, is exactly 0.2663, whatever. And if you're wondering where we got these values from, we got this from a process called automated hyperparameter tuning. So what is that? I'm not going to say it again. Automated hyperparameter tuning is basically, and Don did do this, and that's how we got these values. You take your laptop and you ask it, hey, what are the best hyperparameters for this data using this model? You take the laptop, you sit it in a corner for 4 hours, and you come back after 4 hours, and it gives you incredibly specific numbers. It's going to be incrementally testing different hyperparameters within tiny fractions of each other to see exactly what combination of hyperparameters performs exactly the best. So Don did actually do this, put his laptop in a corner for 4 hours or something like that, and it came back, and these are the exact hyperparameters that are good for this problem. Sorry, I've been talking a lot. So if you want to learn more about it, there's a hyperlink here, but we will go ahead and define this model. So we have a fancier model. We'll go ahead and run this block together to prime it. Now we can actually train it using our data again. So if we run this next code block, we will actually teach the fancier model what stroke victims look like. So we're going to get two variables out of this block. We're going to get fancier preds class and fancier preds proba. So class is basically for every patient, the model will give a 1 or a 0 based on, is this patient going to have a stroke? That's a 1 or a 0. 1, yes, 0, no. The fancier preds proba is risk scores. So what is the likelihood of this patient having a stroke? So let's go ahead and run this block together. It takes a little bit of time to compute, but then we have these variables ready to go. So now you might be eager to see what the AUC of this fancier model is. But before we do that, before we actually just go ahead and spit out that value, let's figure out exactly what kind of math are we working with here. So to reiterate, if we run this next code block here, we can see 41 patients out of 982 actually had a stroke. 41 out of 982, that's less than 5%, so 4 point something percent. It's a very small amount of people. Again, if our model simply predicted, nope, no one's going to have a stroke, then it would get an accuracy of 95 point something percent, but that's not what we want. Instead, we're going to see how accurate it is on a patient-by-patient basis. So this next block here, if we run it, we take all of the top 41 patients according to their risk score, and we display them. So we can see for all of the patients in the testing data, the first 41, we can see what their risk scores were and what their attributes were, and historically, whether or not they really did have a stroke. So let's see what we have at first. So we can see that the absolute top score was assigned to a man. It was an 81-year-old man who has been married before. He has hypertension and heart disease. He has an average glucose level of 250.89 and a BMI of 28. He does smoke. So I don't have a doctor's license, but I do know offhand that those kinds of attributes will lend themselves towards having a higher likelihood of having a stroke. So we gave this person a very high risk score, and that is, in fact, a correct assessment. But let's take a look at the next highest risk score. So we can see here that the next highest risk score was a 65.68%, and this was given to an 80-year-old woman. So she has hypertension, but no heart disease, and a few other attributes, but we can see that historically, she did not have a stroke. So these are the first 41 rows. Why did I choose to display the first 41 rows when ranking by risk score? Well, we had 41 actual stroke patients in the testing data. So in a perfect world, with a perfect model, it would give people who actually historically had a stroke by the time this data was collected, it would give those people the highest risk scores in the data. So all 41 patients who did really have a stroke would have the highest risk scores, and everybody who did not have a stroke would be ranked underneath them. That would be the best model possible, an AUC of 100 or of 1, sorry. But that doesn't seem to be the case. If we look at the first 41 patients based on risk score, we can see a decent amount of 1s, but also a lot of 0s. So it gets a lot of patients wrong. Like, for example, the first woman in this data set, or ranked by risk score, we can see she did not actually have a stroke, but she got a very high risk score. So we can see a lot of 0s and a few 1s. So it doesn't look very good at first. But remember, we want to see, based on AUC, how quickly was it able to find all of the actual stroke patients. So if we run this next code block, we actually straight up just print all 41 historical stroke patients. So everybody who really did have a stroke, what were their risk scores? So we can see the absolute top highest risk score was given to a man, an 81-year-old. We already looked at his data. The fourth highest risk score, because we're 0 indexed, so the fourth highest risk score is a 59.99%. The fifth is at 56.86, so on and so forth. And if we take a look at their overall rankings within the testing data, which you can see based on their index on the left, all of the actual stroke patients are pretty close towards the top. We have 982 stroke patients, which means that the halfway point is 450 plus 42, which means 492. I really hope I'm not getting that wrong. But the halfway point is 492. And all of the actual stroke patients, save the very last one, is in the top half of the data. So it turns out, even though we weren't able to get all of the stroke patients within the first 41 rows, the model is still taking all of the actual stroke patients and pushing them towards the top in terms of risk score. So the model is doing a very good job. The people who actually had a stroke are getting pushed towards the top, meaning they have a higher risk score in general. All of this is to say It's a very long-winded way of saying that the AUC of this model is going to be pretty good. So if we run this next code block, well, we have a few fill in the blanks here first. So we're going to put in a Y test for our first answer here and a fancier preds proba for the second. And if we run this code block together, we can see we attain an AUC of 89.0506%, which is great. This actually outperforms IrisML by about 2%, which might not seem like much, but this was surprisingly hard to get, which, you know, good for IrisML. That means we made a good product. But in any case, we got an accurate an AUC of 89.05%, which is great. This is a very good model for our purposes. Now, to really see how opinionated it is and to make sure it didn't just get lucky, let's go ahead and print out the range of risk scores. So we can see here, it is a much more opinionated model than its predecessor. The lowest risk scores that this model gave to the patients was near 0. So we can see actually in our testing data, we had patients who were as young as like 14, which are, you know, children. They're not less likely to have a stroke. So they're probably somewhere down here. On the other hand, we remember that 81-year-old man who had the highest risk score overall. He got a risk score of around 70%. But we can see that the model is able to say, pardon me, is able to say with pretty good certainty that there are people who are very unlikely to have a stroke. And on the other hand, there are people who are very likely to have a stroke. It has opinions, which means it's a pretty good model. We did a good job. So we have two more things for this part. So the first is a bit of a bonus. So we're going to take a look at feature importance. So basically, we're going to take each of the patient's features and we're going to see how important they were to the model when the model was determining the risk score for a patient. So if we run this code block here, we can see that age was far and away the most important determiner of whether or not somebody would have a stroke, which, again, I don't have a doctor's license, but based on what I know is kind of unsurprising. The older you are, the higher risk of stroke. The next highest assessment, or the next highest feature in terms of importance is heart disease, which, again, unsurprising. And the third highest is ever married. Now, I can't see you because this is a recording, but you might be chuckling at that. Turns out, ever married is pretty much just a proxy for age. The older you are, the more likely it is that you've ever been married in your whole life. This does not mean being married puts you at risk of having a stroke. Kind of like a correlation, causation sort of problem. But in any case, we can see here, lay out very plainly which categories were most important when the model assigned risk scores. And this is also a nice way of showcasing the power of Python, especially of libraries like pyplot. This is a very easy way for people to take data or to take models that they've computed from that data and look easily from a nice pretty graph at a nice overview of what's going on behind the scenes. So all that being said, this very last code block is very important. So this is part G. We're going to export the model. So we're basically going to take the weights of this model, aka it's kind of like a fingerprint of the model, and we're going to output it to a file called xgboost_export.json. And this is so that part 4, led by Alex, can reference it in the next bit. So let's all go ahead and run this block together. So that is my part. Again, you can feel free to scroll through. There's a lot of hyperlinks and stuff like that for you to explore if you'd like to look into more details about what's going on. But yeah, I hope you enjoy the next part, and thank you for participating in this part.
Thanks, Agustin. Hi, I'm Alex MacLeod, and I'll be walking you through part 4, which is to take the two models that were just built in Don's and Augustin's exercises and embedded them into our hospital census application. The way we'll do this is to use two different methods for the two models. Right? So there's an Angular UI, which is that application that you saw in one of Don's slides, and the Angular UI calls a REST service that reaches back to the Iris backend. It then runs a query against the table, our stroke eval table, to get all the fields for the patients. And then using the first model that was created through IntegratedML, we'll simply modify our SQL statement to use a probability clause that will include the risk prediction. And in the second method, we will call an embedded Python method to load the model that Agustin just exported so nicely for us and calculate the probability that way. And then that is passed back as a JSON result to the front end and then displayed in the application. So in approach 1, this is what it looks like, and I'll show you this in a walkthrough in a minute. But the green you see is your standard SQL, and then you add this probability statement to use our trained model to predict, the likelihood that this patient will have a stroke. So that's pretty simple. All you need to know is, standard SQL plus this one specific statement that we have added to the language. The second approach is looks a little bit more complicated, but it uses the better model that Agustin created, and basically use this language equals Python tag to flag your method as a native Python method, and that lets you write Python just like you would anywhere else, like you did in the Jupyter Notebook. And then we have a %sys.python class that provides all of these built-in Python constructs like lists that you can pass back and forth as arguments to kind of handshake between the ObjectScript methods and the Python method. So it's pretty neat how it seamlessly walks back and forth between the two. And the way we're going to calculate the probability in this case is the embedded Python method will load in the model that you just exported in exercise 3. So let's take a look at what this looks like. First, if I go to localhost :8098, you will get the application that Don showed you. It has the patients listed, de-identified with some of their information that you saw earlier, and then it has an empty probability stroke column. So our job in this exercise is to populate that column, and we'll do that 2 ways. The next thing you need to do is, if you go to your zip file contents, there's a file called ml-isc.codeworkspace. You want to double click that to open Visual Code. Now, if you don't have Visual Studio Code installed yet, you can do that. It's pretty straightforward, just to download and install. And what we'll want to do to get some of the neat functionality with the Iris backend is install an InterSystems extension. So we will go to this extension screen here on the left. If you hover over it, it'll say extensions. And then if you type in InterSystems, it should give you a couple of options. The one that we want is this InterSystems ObjectScript extension pack, because that has a couple of sub-extension packs. You'll see the number 3 here. And that'll get us things such as type ahead functionality, proper underlining of the code, etc. So once we have that, we can go back to our Explorer window, and you should have something that looks like this with a src source package. And if you double click the rest.cls, that'll get you the class that we're using for this. Now what you'll see is this is a REST class. Right now it has 1 route and 1 commented route. I'll explain later, but this is basically to flip between the 2 approaches. So right now it's calling a method called IntegratedML. So if you scroll down a little bit, you'll see that method here. It constructs the query to just select the different properties or columns from the table that you're used to. And then we want to add where it says insert code for step A3 below this line. This is where we want to add our probability statement. So I'll copy this so that you guys don't have to wait for my slow typing. And I'll paste that in here. But it'll look like it did in the slide. You're basically adding, as if you were adding another column, but it uses this probability function on our stroke model using the trained model that we created in exercise 2. And it'll return a column called probability underscore stroke that'll be added to the JSON result. That's all we have to do for this approach. The rest of the code has already been prepackaged for you. You can feel free to peruse that later. But basically what it does is it executes the SQL statement then loops over the result set and the different columns, gets those columns back for dates and times. It does some formatting to make sure that gets translated from our internal canonical date format into something that's more user-friendly. And if it has a stroke column, it'll add that. If you hadn't added, the way the UI functions is that if you haven't added your probability statement to the query yet, the application won't fail. It'll still work because it knows that there's no probability stroke result yet. And then it just does some error trapping and it returns the response as JSON. So to compile this, you can press Control S. And if you get an error like this sometimes happens on the first time you do this. If you already had this downloaded before, you did the exercise before and then pulled a new container, it recognizes that there are different versions. You can just say override on server, and then it won't ask you anymore because now this is the current version it'll use. Now, if we go back to our application and refresh that, take a second. And now you have the probability stroke column filled in with these different probabilities, and you can sort by that column as well, from lowest to highest or from highest to lowest. And that'll, let someone who's working the application understand, okay, which patients should we maybe focus on first for intervention purposes or whatever that may be. So now let's look at the other option, to use embedded Python with the model from exercise 3 instead of IntegratedML. Now to do this, we will simply comment out this first route and make sure it uses the second one, which calls the embedded Python method instead. Slow moving cursor in this case. Okay, now let's inspect this embedded Python method it's calling. That's a little further down. Here we go. And what you'll see here is it's very similar. It constructs the same type of query, only this time we will not add the probability statement, because instead we will, later call the embedded Python method, get those probabilities back and add them to our list of patients. So in this case, it just executes the query, and now we have to do some magic to, for each patient, calculate, or for the list of patients, have it calculate the probability for each patient that they will have a stroke. Now, what you'll see here is that I'm referring to this %sys.python class and, constructing one of those built-ins so that I can now take advantage of things like Python lists, right? So I'm in an ObjectScript method, which is typical iris, but I'm already aware that I need to somehow pass this result set that I got from the query over to Python. Only Python doesn't understand any, iris native constructs. So I need to stuff it into something that Python understands. So the first thing I'll do is create a list that can hold all of our patients. So we will copy that in here and say patient list should be a new Python list, basically. And that list will hold all of our patients, including the probabilities. Next, you need a list for each patient, because each patient has, an age, a BMI, a residence type, the different clinical attributes. So you need to stuff those into a list too. So you'll have basically 2 nested lists, right? One for each patient, and then a list of all of your patient lists. So what we'll do here is create another list, and we'll call this one Python patient. And then what we'll do is we basically loop through the results. So we loop through the results set, create a list for each patient, and then loop through the columns and add those to the list. And then at the end, that entire patient will be added to the overall list. So all of that is already pre-built for you. And the only thing we now need to add is, once you have the list of properties assembled for each patient, then we want to add that patient to the overall list of patients. So that will go right here, insert code for step 5. Right, so now that patient is added. And then what we want to do is now call the embedded Python method, right? Because now I have all of the SQL query data added to the lists, but I still need to calculate the probability. So right now I'm instantiating probabilities, and then I'm saying, okay, get them from this embedded Python probabilities method and pass the patient list that we just constructed as a parameter. So now let's find this Python probability method. It's pretty slim right now, but you'll see here the tag that says language equals Python. Then it imports a couple of the libraries that you saw Agustin use as well. And now I'll add a bunch of Python code, and then I'll walk you through what it does. You don't want to watch me type all this. So bear with me 1 second. We'll add this here, and then I'll explain what it does. Now, what you'll also see is the parser knows now, based on this tag, that it parses this according to Python, right? So in here, if I now type something ObjectScript, it doesn't like it, right? Because that's not valid Python. So it's pretty smart in how it switches the context. But what we're doing in here is we're getting the Python list of lists passed in as an argument. And now for the machine learning model to work, we want to stick that into a data frame. So we're creating a new stroke data frame using the pandas library. And what we give it is the list that we just created and passed in as a parameter. And then we tell it what the different columns are, so that it knows what the structure looks like. We have to, recreate some of the code that we also had in the Jupyter notebook to convert the string fields into categorical fields for XGBoost. So it just makes sure that the data types match what we used for the training data. And then what we do is we load the model that Agustin had exported in exercise 3. So this is the xgboost_export.json file. And then it can use that to call this predict_proba method on the data frame we just created. And then we transform that back to a list and pass it back to ObjectScript. And the ObjectScript method, excuse me, scrolling too fast, I'm too ambitious here, can then use that. So we're getting it back here. It loops through the list, so it counts how many entries are in those lists of probabilities, gets each probability, adds it to the list, right? The probability for each patient, and updates the JSON list, and then pushes that back into the response, and then it gets returned to the Angular frontend. So I'll save this by pressing Command S. Now you're not getting that override on server requirement anymore because we've already done that. And then I'll go back to my front end and refresh that. And now you're getting the probabilities again. You'll see now the highest probability, if I sort it again, descending is 69%, more or less, right? So now it's using the embedded Python method instead of the integrated ML method. Both approaches work just fine. So let me go back to the slideshow, but you can do either one, and it's pretty neat because you don't need to necessarily know anything new, right? Either you're familiar with SQL already, then you can use what we created through integrated ML and just, amend your SQL queries to include those results, and that might be fine enough for certain models. Or you unleash your data scientists, you get a nice Python model or something, you import that, and now you just need resources that know how to write Python, and you do that embedded. Now, the advantage of this being we're bringing machine learning directly to the data, right? So you don't have to create these massive comma-separated files anymore that you export and then give to the data science team. It takes 3 months, and you get back, and now you have to make it somewhat functional. And maybe call out through a gateway to some other technology to invoke the model, get the result back, and embed that in the application. None of that is necessary anymore, right? So now integrated ML runs directly in our SQL engine, so you can do it right there. The embedded Python runs natively within the Iris kernel as well. So again, once you create the model and you load that, everything gets executed within the same environment. There's no callouts anymore. So there's a lot of options you have in using, machine learning with InterSystems technologies, and that spans the gamut from, the early work, some of the feature engineering, to integrated ML, to embedded Python. So you can take a couple of different approaches here. I think we try to make it very easy to bring all of that together and give you freedom of choice in what you're comfortable using, what you're comfortable with the output, and what you trust, and then embedding that into your application. We've used a couple of different technologies in the session. You could either use InterSystems Cloud SQL or the management portal with your on-premise Iris installation. That's what we walked through here. We've used integrated ML, and we've used embedded Python, as well as the external piece using Jupyter to kind of create that more advanced model. So we hope you had fun. We hope you can recreate this on your own and get inspired with some ideas of how you could use it, but feel free to contact us anytime. Thank you.